right? Yeah. Okay. In fact, usually that's one of the, there's about 3 or 4 things that separate the people that show up in this class versus the people that don't. One of them is stoichiometry. So there you go. Let's just do this one. Let's take some method or propane. Anyone know the formula for propane? Just off the top of your head, you may not. It's okay if you don't. You're not fired. You guys know of propane, yes? It is. How did you know that? Remember from last year? Cool. Yeah, you guys did like what, a week and a half, maybe? So we're going to take some propane. What state of matter is propane? It is a gas, okay? How many of you were thinking it might be a liquid because you've picked up a propane tank? Has anyone picked up a propane tank before? Did it slosh around? You don't remember? Okay, do you remember?
It didn't slosh.
Well, that's probably because it was empty. Might have been empty. But anyway, in the tank, it's actually liquid because it's pressurized. Okay, and then obviously if you open up the valve, it releases that pressure, becomes a gas. So anyway, it is a gas. Oh, we're going to burn out with a little oxygen so everybody knows what the products are going to be.
Water.
And
Some carbon.
I hope no carbon. Possibly some carbon dioxide, hopefully. All right. I want you guys to spend a quick 14.38 seconds balancing that. Okay, now you're down to 10 seconds. $4.37 now. And Alicia, what do you have? Just just read off the coefficients. 1663. Everyone concur? I don't either. I don't know. Oh, you could be right. I don't think you're right.
Oh, wait, I'm wrong.
Yes, you're wrong. Go ahead. 1543. Anyone concur with that? Yeah. Listen, this is no-brainer stuff. I mean, not that. I meant the stoichiometry thing I'm about to go through with you guys. The one thing I have noticed, though, with a lot of students who come from home class, it seems like you guys did almost all your stoichiometry you guys did is mass problems. And then when we start even giving you moles or asking you to find moles, you kind of go, I don't know what to do. So ultimately, for this class, most of the stoichiometry we're going to do is going to be mole problems for reasons that you're not aware of yet. But, anyway, so let's do this. Let's say, I don't know, Jonah, pick one of the things. I don't really care. Carbon dioxide. I gotta go buy markers. And Jama, pick another substance. I don't care what. There we go. So, how do we recognize this as a reaction stoichiometry problem? It's a rhetorical question. One, you're given a chemical reaction. You may or may not have to have balanced it. All reaction stoichiometry problems, though, do utilize a balanced reaction. So if it's not balanced, you should balance it, okay? Secondly, we know it's a reaction stoichiometry problem because we were given, whoa, that was silly. What I have, 0.042?
Yeah.
I got ahead of myself. 0.402? That was dumb. I was really dumb. Sorry about that. I was thinking limiting reactants already. So in this case, we're given the amount of one of the substances, asked to find the amount of something else. You can technically find the amount of any other piece given, or all other pieces just given one thing. You guys knew that, right? Assuming a 100% efficient process. Now we're going to find out here in the really near future that not all processes are 100% efficient, but we're going to go with that assumption now. So anyway, given this, find that. Always start with your given. In this case, be 0.402 moles of carbon dioxide. The little tool that we use to switch over from one substance to the other is called everyone together now. How do we switch over from carbon dioxide to oxygen? There's a factor we call the mole ratio, which comes from the Balanced equation. And in this case, there are 5 moles of oxygen for every 3 moles of carbon dioxide. You guys knew that. You forgot. Moles of carbon dioxide cancel. I'm down moles of oxygen, but I'm looking for grams of oxygen, so I need to convert that to grams. Does anyone remember what oxygen is? Molar mass for oxygen?
16.
Nope. What's that? 32. It's 16.
Oh, it's 16. Yeah.
But I let that happen on purpose because you guys will occasionally still forget. Okay. And wasn't there a diatomic question on that assignment I gave you? Well, it wasn't asking you what the diatomics were, but it was asking you if it was it a molecular element, I think was something you had to say, which basically are saying the diatomics. So 32. And without touching our calculators that you have all done so far. Let me see, who are my, I'll let Annie be a calculator person today because she has sitting there, and it looks, you had yours out the last time too, didn't you? Yeah, go ahead. No. You practice anyway, you play along with us? Okay, you play along with us. So let's come up easily within one significant figure. Oh, gosh, this one's easy. There, done, all right. Wow, that was easy. Easily within one significant figure. Kaylin doesn't know that I'm going to call on him yet, but I'm going to call on Kaylin. Do you have an answer yet in your head? No? Can you have an answer in your head here, Richard? What's the answer to this problem? Oh, okay. 1 point something? 21 point something. Anyone concur? Okay. That's even better than one significant figure. Well, what do we have? 50, 24. Yeah, I'd say 20.
About
20 something. Would you guys agree with that? Okay, so does anybody actually do it? Did you, Maddie? What'd you get? 21.44. I disagree. That's close enough. Okay. Does everyone remember how to do this? Well, we'll find out. I'm going to have you try one on your own. Colin, pick a substance, any substance.
acetate.
Try again.
What?
Nothing.
You said try again?
I did. Ashton, pick a substance. There's no carbon up there. Pick a substance. Pardon? Water. Okay.
I didn't know you wanted one that's you wanted me to pick one that's already on the board. I thought you wanted
And let me see. Pick another one.
C3 or
propane. Okay, ready, set, go. You forgot to tell me, Casey. Oh, let me see. All right. Let me see. Holly, what do I start with?
The 39.42 ratio.
Okay. And Jared, what'd you do next? And Ashton, what did you do next? Maybe you didn't do it this way. Did you guys do stoichiometry? You never did this. Yeah, you did.
Very little bit.
Okay. Lauren, what did you do next? Okay. Jamie, did I call on you? I already called on you. Who I need to call on? Alex, what did you do next?
The bowl.
Yeah, what did you put?
1/4.
Okay, 1 mole of the propane over 4 moles of the water. Make sure you're labeling everything appropriately. And oh, I'm done. Oh, geez, that's why it's not 20. I went ahead and converted to grams. Hold on. Yeah, it's like 0.45-ish. 0.54. So 0.5469. Okay. Are we remembering stoichiometry now? Awesome. Again, for some of you, it's been a couple of years, so I just wanted to revisit that fairly quickly. If you forgot, I'm sure it won't take too long to catch back up. Can I erase that? Okay. Next, let's come up with a different reaction. Kind of title that way. I actually have one we can use. what if you were provided with and you're asked a question such as this. Does it appear to be a stoichiometry problem, reaction stoichiometry, where you're given some stuff, asked to find something else in a chemical reaction? Yes, definitely. However, what do you notice about what you're given? You're given the amounts of all of the reactants, right? So, unless it ends up being an exact stoichiometric proportion, meaning there's the exact amount of both of those things that you want, one of those things is probably going to run out before the other one does. Hence the limiting reactant thing, you guys all knew about that, right? Now, when Mr. Homan showed those of you that had him, you were almost guaranteed to have to do 3 stoichiometry problems if the 2 questions that are typically asked were asked. The 2 questions are, how much product can be made and how much of the excess reactant is left over. Does anyone vaguely remember those 2 questions? Okay. Well, the way some of you were taught, you had to do 3 stoichiometry problems, guaranteed, to answer those 2 questions. I'm going to try and show you a way that you might get lucky and only have to do 2. And actually, I'm going to show you another way that I haven't even shown my students yet, that's going to be very helpful as we go down the road here, that you may only have to do 1, which would be cool also. Okay, because it's a time-consuming process. Would you guys agree? You guys remember getting a little frustrated? It took forever to do that. All right, let me show you the way that you might get lucky and only have to do 2 stoichiometry problems, which is different than what many of you have been exposed to. I'm just going to randomly ask someone I haven't called on yet today, and I'm not even sure who that might be. Grace, have I called on you yet today? Good. Pick one of the reactants. It doesn't matter which one. There you go. She went with the ammonia. By the way, you knew that was ammonia, right? We'll go with that. Okay, she went with the ammonia. So what we're going to do is, hey, let's do a stoichiometry problem between the ammonia that she picked and the copper 2 oxide to find out how much of this copper 2 oxide we actually need. Okay, so here we go. So we take the 18.1 grams of ammonia. Of course, everyone remembers that its molar mass is 17.04 grams per mole. And then, of course, we know the mole ratio is right there in front of us. So it's 2 moles of ammonia. Now, copper 2 oxide. Copper is 63.55, I think, and oxygen. So we're looking at 79.55. Someone can check me on that. Does that all look somewhat familiar? Doing the process is what I'm saying. Okay. A 120-ish. It's going to be right around 120-ish. And somebody can do that real quick. Want to come in and learn some stoichiometry? No? Okay, well, she'll wait a couple months. Now, what does that mean? That means that for every 18.1 grams of ammonia, I need 126.75 grams of copper 2 oxide to completely react with that ammonia. Everyone understand that whole concept, right? Do I have enough copper 2 oxide? I do not. So which one's my limiting reactant? The copper oxide. You can see how that works out? Isn't that kind of cool? Now, I think you can imagine this. What if, I forget, was it Grace? What if I had had Grace pick, by the way, Grace got unlucky. Remember I said you have a chance of only having to do 2? we're going to end up having to do 3. But that's okay. I want to show you what could have happened. What if she had picked the copper 2 oxide? Now I'm just going to do that one. Anyway, you guys don't have to write this one down if you want to. Okay? But let's say that she did pick that. I'm kind of doing it in ink that you can't see, that way, you know, it's not there. Let's go buy some markers. We'll pick up there tomorrow. Done currently is figure out which one's limiting. We still have to figure out the mass of product. That's easy. So we take our limiting reactant, as always, which is the 90.4 grams of copper oxide. Grace decided to pick the ammonia for the same reason that most of you would have decided to pick the ammonia, because it had the least amount. You're thinking, limiting, right? Right? Is that what you were thinking?
Sure.
I don't know. I'm just asking. Okay? But that's not always going to be the case. Anyway, so now we just do our normal things, 79.55 grams, mole ratio, and of course the mass of nitrogen, which is 28.02 grams. And relatively quickly, 0.125 times 100. We're going to be right around a little over 1. Give or take a little bit. Or sorry about that, not 110. I got to do my decimal point appropriately. Right around 10-ish. 10.65. And we would be limited to 10.7 due to significant figures. Okay? Now, going back to asking that one question that ends up being asked a lot, how much of the excess reactant is remaining? Well, once again, based on Grace's original decision, we would have discovered, oh shoot, I don't know how much ammonia was actually required, so I'm going to end up having to do that third stoichiometry problem. However, if someone had decided, hey, I'm going to start with this, you can see I would have still figured out which one was limiting, but I would not have had to have done that stoichiometry problem. So you got a 50-50 chance of only having to do 2, which is better than having to do 3 every single time. And then, like I said yesterday, you guys got to keep reminding me of this. Grace, didn't I put this on you? Say this again. I'm sorry, what's that?
The 2 as in...
The 2 that you are going to have to do is 1 final limiting reactant and 1 final product.
Okay.
You may not have to do that third one depending on how lucky you got. Right. Whereas before, I think you learned to do all 3 of them every time.
Yeah.
Because I think you guys went to the products both times, figure out which one make less, the least, and then went back and did that third one. So I'm trying to give you a chance. Okay. But wait, there's another way. And this is really going to come into handy when we start doing solution stoichiometry where everything's in moles. Remember using molarity and volumes and stuff like that, you can get to moles. This becomes really handy. Not as handy when we're dealing with grams, but it's still handy. And technically, you're only going to have to do 1 stoichiometry problem, maybe 2. So anyway, what I would do is just convert everything to moles. This is an alternate method. Okay? Convert everything to moles. I don't even know. Oh, yes, I do. 1.062. I actually have these already. This is the way I did it. And now, it's not always going to be this cut and dry. And so I'll show you what to do if it's not that cut and dry. But there's the moles of ammonia that the 18.1 grams represents. There's moles of copper oxide that the 90.4 grams of copper oxide represents, okay? We can look at this, and I think relatively easy, look at the mole ratio and decide which one of these is going to be the limiting reactant. Now, I know you already know the answer to that, but can you guys clearly see that we don't have enough copper oxide? I need 50% more copper oxide than I do ammonia, based on the mole ratio. You guys agree with that? 3 to 2, right? 50% more. Do I have 50% more? I don't. You can pretty clearly see that the copper oxide is the limiting reactant. So we haven't done a single stoichiometry problem on paper. We kind of did it in our head a little bit. But we can see that we have copper oxide is the limiting reactant. Now, some of you are a little like, oh, I'm not sure if I would be able to make that decision that quickly. So here's a little thing that you can do if you're not sure or if it's closer than what it actually is right now. What I would do is say, okay, I'll take my 2 moles of ammonia, which is over 3 moles of copper oxide. Of course, what does this represent fractionally? 0.67, right? 2/3, 0.67 to 1. And then I would just divide these two, okay? And you're going to come out to be just under 1. I don't know what that comes out to be. 0.93. This comes out to be 0.93 to 1, okay? So I clearly have more ammonia than is required. Copper oxide's limiting. So far, so good? Okay. That's a way you can look at it also. That really becomes handy, like I said, when we're doing solution stoichiometry with polarities and everything. But either way, there you go. Provide some evidence as to how you got this is the main thing. Okay. How much excess reactant is there? Well, remember we would have had to have referred to that green calculation that we did. The amount of excess. Would have been the 18.1 grams of ammonia that was present. And we subtract from that the, was it 12.6 or 7? I can't remember. Nobody did the green. What was it? 12.9. Okay. Minus 12.9 grams of ammonia required. And then obviously that comes out to be 5.2. And that's it. I'm going to guess that the majority of you, even if it's been 2 years, remember the process of doing this. It's probably might take you a time or two to get back into the game a little bit. I mentioned something about the next assignment being due. Did I say Friday or did I say Monday? Yeah, I hope. Yeah, we'll keep it Monday. That'll be plenty of time. I am going to. You see, today is Wednesday. You are going to be busy in class for the next 2 days doing things other than that assignment. So the assignment is intended to be worked on your own for the next 5 days or whatever it is. And hopefully, by tomorrow, I'll tell you whether or not you're going to continue needing to bring your books or not.